Okay, got a question here about, let's see, chapter 29, number 47. And so let me give it a try here. It says that the protons have a kinetic energy of 5 mega electron volts, MeV, okay? And they are moving in the positive x direction. All right, so I'll put a little p, proton moving in this direction. Their kinetic energy is 5 MeVs. They enter a magnetic field area. So let's make kind of a little box here, kind of shown in the picture. So this is the magnetic field. Actually, they put a little dot there indicating that the magnetic field is upward. So maybe I'll grab my green marker here and say, okay, it's up, up, up. Okay, so here's the magnetic field. The dimensions here, what did it say here? Magnetic field that has a value of 0.050 in the k-hat direction. And, of course, units of Tesla. Okay, so it's pointing upward. They're indicating that also here with the math here, if this being the x direction, this being the y direction, and coming out of the paper being the z direction. All right, so coming out of the paper, they say that the field extends for 1 centimeter. They say it's out of the paper, it's extending from 0 to 1 centimeter as shown. Calculate the y component of the proton's momentum as they leave the magnetic field, and B, find the angle alpha between the initial velocity vector of the proton beam and the velocity vector after the beam has emerged from the field. All right. So this boils down, I hope, to the big picture of what chapter 29 is about, that there is a force on a moving charge in a magnetic field, and it is dictated by this equation. Now, let me take this as an opportunity to review some Physics 121 stuff. If you have an object, and let's say it's moving in this direction, if you apply a force in the direction it's moving, that makes it go faster. But if you apply a force perpendicular to it, that does not change its speed, it turns it. And maybe by an extension of that, if we apply a force opposite to the direction it's moving, that makes it go slower. But the point is, the part of the forces that's in the motion or anti-motion of the object makes it go faster or slower. But a force that is perpendicular makes it turn. This is our circular motion from our mechanics. It would be chapter 6 in the Survey book, and I guess also chapter 6 in the OpenStax book. And I bring that up because when we come back up here and apply our Physics 121 to this equation, we can see that. And again, I guess this is the cross product, part of Physics 121. It would be a cross product of our vectors. I think the OpenStax does that in Chapter 2, and I think the Survey does it in Chapter 10. And they do this cross product. But the point here is that the force is perpendicular to the plane of these two vectors. So in other words, the force is perpendicular to the velocity. So I'm talking about a force like this. And so this would make it turn and be part of a circle. This would always make it turn. It would never make it go faster and never make it go slower. That's what this says. And so there's not a whole lot really to add new from this semester about that, but it is a crucial part of this problem. And this is going to get kind of long here, so maybe I'll put page 1 here, is to realize then that this proton, this charge, any moving charge in a magnetic field is going to have a force, and it's going to go in a circle, or at least a piece of a circle if it doesn't have enough space to make a whole circle. And that's what we're going to have here. Now, I bent it down. I should double check that. I didn't really look too closely at it. Let's see. The fingers would go in the direction of the velocity vector. So that would be this way with your palm pointing up so you can close it. And so, yeah, that would make a force downward. Then as it turns a little, this would always be the direction of the force. So this force would always be pointing towards the center of the circle somewhere over here. And that's our motion of a charged particle in a magnetic field. That was the whole discussion. I believe that's section 2 of our Survey book. And I think even also the Open Stats book of this chapter 29 says what motion would a charged particle make in a magnetic field. And we came up with that helix pattern because if it was, perpendicular, it would just be in a circle, and if it had a little component in the same direction as the magnetic field, it would just make then a helix. All right, so that's going to be a big and crucial step here because, again, taking this to be the magnitude of the force, we would get a Q, a V, a B, and then a sine of 90 degrees. As you can see, when it enters, its motion is this way and the field is up. That's 90 degrees. And as it bends, the velocity is still always 90 degrees. That is, the velocity is in the plane of the paper, but the magnetic field is always up out of the paper. So that's always going to be 90 degrees. So that's the magnitude of the force. And again, this is where the physics 121 comes into play. This would have to equal to mv squared over r. And let's see, there's a v on both sides. And so we get this QB, and we know those two. The charge, because it's a proton in the magnetic field. We know it's proton, so we know its mass. Now, its velocity we know, but not maybe directly, and we got to do a little work there, but that's going to allow us then to get the radius. So QB, mv over QB would be the equation for the radius of this circle. And so let's take a little moment here then to talk about the velocity of it. Again, that goes back to physics 121. We know that the kinetic energy, 1/2 mv squared, is its kinetic energy. And that's what they meant when they said it had an energy of 5 MeVs. And so this has to equal to 5 MeVs. Now, to make units match, let me put a 5. The M means a million, mega. And an electron volt is a nice unit of energy. It's actually the energy that you get if you accelerate, and that's why it's called an EV, a 1 electron through 1 volt. And so if we go back to chapter 25, where the energy is QV, so a charge of 1 electron and a voltage of 1. And so if you multiply those together in units of joules, you would get the charge of the electron, 1.602 times 10 to the minus 19 times the 1 volt, giving you 1.602 times 10 to the minus 19 joules. So grabbing my calculator here and saying, okay, this would be 5 million times 1.602 times 10 to the negative 19. And so 8.01 times 10 to the negative 13 joules is the kinetic energy in joules instead of MeVs. And then this side of the equation, I have the 1/2. I'll need to look up the mass of a proton. That's that 1.67 times 10 to the negative 27 kilograms times V squared. And so that's what I was saying earlier is, okay, I'm going to use the kinetic energy, and that is the physics 121, to get this velocity. And so then I can get the radius when I set the centripetal force equal to the magnetic force. All right, so using my calculator here, that number times 2 divided by 1.67 times 10 to the negative 27. And now taking the square root of all of that, I get about a 3.10 times 10 to the 1, 2, 3, 4, 5, 6, 7 meters per second. So about 10% the speed of light, which is why this problem said, don't worry about relativistic effects. And those of you who've gone through Physics 123 might recall that we learned near the end of it in what we call modern physics that these equations by Newton are great, except they have some imperfections. That is, they're not complete, and it's noticeable when you get to about 10% the speed of light. So we say once you start getting to 10% the speed of light, you need to consider relativistic effects. So I'm glad they say ignore relativistic effects, because I'm right there at that boundary. And it wouldn't be a fair question to those of you who haven't gone through that yet. All right, so that's what I would say is really mostly 121 stuff, but obviously this added piece here of what is the magnetic force. So again, set the magnetic force equal to the centripetal force, and of course now you can get the radius. So now we know it's going to go in a circle of a radius of, and I can put my 1.67 times 10 to the negative 27 kilograms for its mass, its velocity 3.10 times 10 to the 7th meters per second. Its charge of 1.602 times 10 to the negative 19, and its magnetic field at 0.050 Tesla. Okay, so putting in those numbers, 1.67 times 10 to the negative 27 times 3.10 times 10 to the 7th divided by 1.602 times 10 to the negative 19 and 0.05. All right, so it looks like we've got a radius of about 6.46 meters. And so maybe just to kind of redraw this picture, he'll be my little area of a magnetic field. I'll enter somewhere about here. And then, of course, that's where we said we know it's going to then follow along the arc of a circle where there's some radius back here, and that's that 6.46 meters. Okay, so it would have kept going out like this. Instead, it's angled down. And that is this question. It says, calculate the y component of the momentum. Now, maybe it seems like it might be easier to do b first, because if I called this angle here, because that's what b is, find the angle, and they call it alpha, between the initial velocity vector of the proton and the velocity vector after the beam emerges from the field. So let me find that alpha, and maybe I will begin by drawing a line straight across, because that's we know to be 1 centimeter. And I have a perfect recipe here to find this angle, right? This is, I got the radius and I've got the opposite, so I can find the sine of that. But I'll do you even better here, because, you know, what is that angle? And it might take a little bit of geometry here, but if you maybe draw this as a straight line here and tangent to this circle here, okay, this being alpha, this being a radius, this is going to be then 90 degrees. And so this right here would, of course, make the third angle where all three of these have to add up to 180. So if we take 180 and subtract this 90, this then is 90 minus alpha. And since we just made a right triangle out of that, that would make this angle alpha. So what's nice about this triangle I have here is it's going to allow me to find this alpha here. So sine of alpha would be the opposite, the 1 centimeter over the 6.46 meters. And so grabbing a calculator here, I'll go inverse sine 0.01 divided by 6.46, and I get an angle here. Oh, I better check what mode I'm in. Mode. Where is it? Ah, there it is. Good, I'm in degrees. So this is a 0.089 degrees. So not much of an angle. Obviously, a really small angle, but enough to. Oh wait, let me reread this. If I might have read this. Well, I lost the problem now. Where's the problem? Homework, here we go. 1 meter. Yeah, my apologies here. This is 1 meter. 1 meter. So this is a little bigger. Yeah, it kind of matches my picture. Well, I don't know where I got a centimeter. It looks like I wrote it here. So my bad. It's 1 meter. Okay, so somehow I got centimeter plugged in my head. But good, I'm glad I noticed it before I went too far here. So let me try that again. Inverse sine of 1 meter divided by 6.46 meters. Okay, yeah, so 10 times bigger. Okay, 8.9, and I suppose we can round it up to a 1 degree. All right, so that's this angle, and then I guess that is the answer to part B. What is the angle? Now, to finish this problem and go to A, page 3 here, is I'll take something that I said earlier in mind, going back to our Physics 121, that a magnetic force, right, according to this math, being perpendicular to the velocity, means it only turns it, makes it go in a circle. It does not make it go faster or slower. So what I would know then is when it's exiting here, it's going to have the same velocity as when it entered. It's not going to go faster, not going to go slower. So to get its magnitude of its momentum, mv, I would just take its mass, 1.67 times 10 to the negative 27, and multiply by its speed of 3.10 times 10 to the 7th. And so that would be its magnitude of its momentum. Now, since it asks for its y component, that would be the sine of alpha. Okay, so the sine of 8.91, which, of course, we know to be 1 over 6.46. So we could just write that as 1 over 6.46. That's how we figured out this angle to begin with. And I guess you might say that would be down. So if we wanted to be technical with our direction of our y component, and we probably should, we're going to have, this is going to be a negative component. All right, so putting in our numbers, 1.67 times 10 to the negative 27 times 3.1 times 10 to the 7th, and then finally times 1 divided by 6.46, I get a component of 8.01 times 10 to the negative 21. And the units would be kilogram meter per second. And I suppose if we want to put a y component, we should then say this is downward in a negative direction here. And that's it.